Welcome. In this demo, we introduce the FOGUS Service Mesh-Enabled Core Network, which is developed in the context of origami. It demonstrates how service mesh technologies can help address some of the challenges of modern 5G networks, which are expected to support billions of connected devices, critical services, and highly dynamic applications. To meet these demands, operators need a core network that is not only scalable, but also secure, observable, and resilient. The evolution from previous mobile generations to 5G has increased the complexity of the core network. More devices are connecting to the network, more services are being offered, and more interactions are taking place between network functions. As a result, signaling traffic continues to grow. One of the key innovations of 5G is the service-based architecture. Instead of relying on strict interfaces, network functions communicate through HTTP-based services. This brings flexibility and programmability, but it also means that every operation generates additional signaling exchanges throughout the core network. As operators introduce network slicing and support diverse applications, the number of network function instances increases significantly. Every new slice adds additional interactions, making the communication of the network more demanding. At the same time, 5G is becoming an open platform. Through mechanisms such as CAPIF and network exposure functions, external applications can interact directly with the core network. This creates promising business opportunities, but it also introduces even more traffic into an already busy environment. Unfortunately, many network functions are still implemented as monolithic applications. Communication, security, routing, and business logic are coupled together. This creates scalability limitations. It also reduces flexibility and increases the impact of failures. All these pain points describe Barrier 8, which is related to high volume of control plane signaling. To address these challenges, the industry introduced the Service Communication Proxy, or SCP. The SCP simplifies communication between network functions, supports load balancing, improves service discovery, and helps manage overload situations. While the SCP solves several problems, deploying it as a centralized component can create new bottlenecks. As networks continue to scale, we need a more distributed approach that preserves performance while maintaining all these benefits. Instead of concentrating communication intelligence in a single component, we distribute these capabilities across the entire infrastructure using a service mesh. Network functions focus only on their business logic, while sidecar proxies handle communication, security, routing, and observability. The result is a cloud-native 5G core architecture where communication becomes programmable, observable, and resilient by design. Let us now look at the building blocks that make this possible. The FOGUS platform combines open-source 5G technologies with modern cloud-native tools. Each component contributes to creating a fully observable and controllable network environment. At the foundation, Open5GS provides the 5G core implementation, while Uransom generates realistic user and radio access behavior as a UE and GNB respectively. Together, they create a representative 5G environment for experimentation and validation. Above the core network, Istio provides the service mesh capabilities, while Kiali visualizes traffic flows and service interactions. This layer gives us visibility into how network functions communicate. Then, Prometheus continuously gathers performance metrics, Kepler measures energy consumption, and OpenCAPIF enables secure exposure of network services to external applications. All collected information is presented through Grafana dashboards. These dashboards depicted in a custom Python application which allows users to execute their experiments, collect and demonstrate the results. It also gives the opportunity to users to monitor the behavior of the entire network in real time and make accurate decisions. Having seen the architecture of the platform, let us move to the operational view and explore how these components work together. The experimentation dashboard continuously monitors every interaction between network functions. This level of visibility enables rapid troubleshooting, optimization, and anomaly detection. Operators can dynamically set the duration of the experiment, the number of UEs and other parameters to execute their experiments without modifying the network functions themselves, increasing flexibility and reducing operational complexity. Real-time performance monitoring allows us to understand how signaling traffic affects the network and how different NFs respond under varying conditions. The platform also measures energy consumption. Understanding the energy impact of network behavior is very important since operators seek greener and more sustainable infrastructures. To explore and test the capabilities of the platform, we had to design a practical resilience scenario. The scenario is based on a distributed denial-of-service type attack named registration flood. More specifically, a group of UEs repeatedly registered and deregistered from the network. Each individual UE request is harmless, but together they generate a flood of control plane signaling. Resource consumption increases, energy usage rises, and legitimate users may begin to experience service degradation. The FOGUS platform continuously analyzes signaling behavior during the experiment. When abnormal activity is detected, the system identifies the malicious UEs, and if the fair use policy is enabled, mitigation actions will take place. The median-based detection algorithm identifies sustained abnormal signaling and applies temporary rate limiting at the Kubernetes pod level. The heat map represents the interaction among NFs before and after the anomaly detection and the mitigation framework. Without anomaly detection, the registration flood causes uncontrolled spikes in signaling traffic and resource usage, mainly impacting SCP, AMF and SMF. On the other hand, when the fair use policy is enabled, the signaling load is reduced, and it stabilizes resource usage without permanently penalizing demanding but legitimate traffic. This demonstration shows how service mesh technologies can transform the operation of future mobile networks. By combining observability, intelligent traffic management, and automated mitigation mechanisms, the FOGUS service mesh-enabled core network provides a foundation for more resilient, efficient, and autonomous 5G infrastructures. For more information about Origami, please visit the project's website, where you can access the public deliverables and learn more about the project's results. Thank you for watching.